All right, let's dive into one of the most just mind-bending ideas in all of physics. It sounds like something straight out of science fiction, right? But believe it or not, it's as real as the device you're watching this on. We're talking about the very fabric of time and the fact that it can actually be bent.
So let me ask you a question, and it's a wild one. Could an airplane ticket literally make you younger? I mean, could you actually fly around the world, step off the plane, and be measurably physically younger than someone, say a twin, who stayed right here on the ground? Well, the answer, and this is going to sound crazy, is yes.
And no, this is not just some fun little thought experiment. This is a real, testable prediction that came straight from the mind of Albert Einstein. See, his theories of relativity, they uncovered something absolutely profound. The time, it's not this rigid, universal clock just ticking away at the same rate for everybody everywhere. Nope, it's flexible. It's a relative.
The key concept we're talking about here has a name. It's called time dilation. And honestly, it's a bizarre idea that you can take two perfectly good, perfectly synchronized clocks, and they can just fall out of sync. They can end up showing different times. And it all comes down to two main things. One, how fast you're moving through space, and two, how much gravity you're feeling.
Okay, so here's where it gets really interesting. For anyone on an airplane, these two effects are locked in this kind of cosmic tug of war. You've got one force from Einstein's special relativity that's pulling on time, trying to slow it down. And then you've got this other force from his general relativity that's pulling in the opposite direction, trying to speed it up.
So you've got these two competing forces, right? Speed versus gravity. Special relativity says the faster you go, the slower time gets. But general relativity says the higher up you go, where gravity is just a tiny bit weaker, time actually speeds up. So for our clock flying around the world, which one is going to win?
Okay, to get our heads around the speed part, let's picture something called a light clock. Imagine a little photon of light just bouncing between two mirrors. For Alice, who's holding the clock, that photon just goes straight up and straight down. Super simple, right? But now imagine Bob is watching Alice fly past him at high speed. From his perspective, that same photon has to travel a longer, diagonal path to get from one mirror to the other. And here's the kicker, the absolute rule of the universe. The speed of light is constant for everybody. So, if the light has to travel a longer distance for Bob, but it can't speed up, well, it has to take more time. He literally sees her clock ticking slower. Mind blow.
Okay, if you thought that was weird, the gravity part is even wilder. Let's imagine Alice is at the top of a rocket that's accelerating upwards, and she shines a light down to Bob at the bottom. While that light is traveling, Bob is actually accelerating towards it. What does that do? It kind of squishes the light waves together, making them appear blue-shifted, which just means a higher frequency. And a higher frequency means, well, his clock is effectively ticking slower than Alice's. Now, here comes the genius part. Einstein's big insight was that gravity is basically the same thing as acceleration. You can't tell the difference. So being higher up in a weaker gravitational field, it's just like being Alice at the top of that rocket. Your time ticks faster. So all this theory is fantastic, but how in the world do you actually prove it? Well, back in 1971, two scientists, a physicist named J.C. Hafele and an astronomer, Richard Keating, decided they were going to put Einstein to the test. And their plan was, well, it was brilliant and honestly pretty audacious.
Get this, their entire budget, the money they got from the Office of Naval Research, was just $8,000.
And to put that into perspective for you, almost all of it, we're talking $7,600, was just for the plane tickets. They were about to run one of the most important tests of relativity in history on what was basically a shoestring budget.
But their method was it was beautifully simple. They took 4 super accurate cesium atomic clocks and synced them all up with a master clock at the U.S. Naval Observatory. Then they just put them on commercial jets and flew them around the entire world. First they went eastward, then they turned around and went westward, and my favorite part of this whole story, they actually bought seats for their clocks under the name Mr. Clock. I love that. So after all the flying was done, they brought the traveling clocks back to the lab to see if they were still in sync with the one that stayed home.
So, this was it. The moment of truth. You have decades of these completely mind-bending theories about to smash right into hard, cold, experimental data. We're talking measurements in billionths of a second. So what would it be? Would all the clocks still be in perfect sync? Or would they prove Einstein was right all along?
Okay, and remember that tug of war we talked about? This is where it becomes absolutely critical. See, when you're flying eastward, you're moving with the Earth's rotation. that means your total speed is really, really high. So the prediction was the speed effect, slowing time down, should dominate. The clock should actually lose time. But flying westward? Now you're going against the Earth's rotation. Your overall speed is lower, which means the altitude effect, the one that speeds time up, that one should win the day.
And here are the results. Check this out. For the eastward trip, the one with the high speed, the theory predicted the clocks would lose about 40 nanoseconds. The actual measured result? They lost 59 nanoseconds. Wow! Now for the westward trip, where altitude was supposed to be the big player, theory predicted a gain of 275 nanoseconds. The measurement? A gain of 273. Within their margin of error, it was a perfect match. So let's just let that sink in. The clocks that flew eastward landed, and they were 59 billionths of a second younger than the clocks on the ground. They had literally lost time.
And the westward flying clocks? They were 273 billionths of a second older. They had gained time. There was no other way to explain it. Einstein was right. Time is absolutely relative.
That is just an incredible result. But, it does raise a pretty fair question. Okay, it's fascinating science, but does any of this actually matter to you and me in our daily lives?
Really, who cares about a few billionths of a second? It sounds like the most academic, nerdy, trivial thing you could possibly imagine, right? Well, it turns out you care. You care a lot. Because that smartphone in your pocket, it relies on GPS. And GPS, it only works because we understand relativity. Think about it. Those GPS satellites are moving incredibly fast, which makes their clocks slow down by about 7,000 nanoseconds every day. But they're also way up high in weaker gravity, which makes their clocks speed up by 45,000 nanoseconds a day. If the engineers didn't constantly correct for that net gain, that's 38,000 nanoseconds, your phone's GPS would be off by 10 kilometers. Not in a year, not in a week, per day. It would be totally useless within minutes.
So yeah, the next time you pull up a map on your phone to find the nearest coffee shop, just take a second to remember Mr. Clock and the experiment run by Hoffley and Keating on an $8,000 budget. They prove that the things we take for granted, the fundamental rules of our reality, are way stranger, way more flexible than we could ever imagine. And that leaves us with one last big question. If time itself can be bent and stretched, what other fundamental rules of reality are just waiting to be broken?